Yeah, it was cut off. Okay, try 800 by 600.
Again?
Yeah, let's just see. So let's go back to 800 by 600.
1024 by 768. 1024 by 768. Is that what you're trying to find?
We were actually just trying to get 800 to 600, 800 by 600 working.
Can you do 1024? Because that's what the projectors are opted to be done for. Well, anyway, you still do it. There you go.
1024.
Yeah,
This one?
Yeah. Let's do the programming.
Steve. So it looks like the width is okay. Let's see if we can get the bottom.
Yeah, listen.
Okay.
An hour? That's an hour.
No. You can be a little bit flexible. It's not super tight.
Yeah, I think I have more slides than I can skip some. I guess people can ask questions.
Yeah.
Sure.
All right. It's my pleasure to welcome Morley Mao from Michigan. Morley, been there 5 years.
Yeah, 5 years.
Been about 5 years, and Morley works on a lot of topics related to internet, particularly internet routing and security and measurement, things like that. And she's had the opportunity to work with a quote-unquote tier 1 ISP for many years.
Mm-hmm.
And so a lot of the work that she's been able to do, she's been able to take advantage of that collaboration and use data and results applied to real large-scale ISP. Really helps make the work very practical and relevant to the internet that we're living with today. And so today, Morley's going to talk about a number of projects that have been done over time dealing with measurement, because before you can fix the network or make the network work better, you have to be able to understand how the network works. So measurement
Oops.
is always one of the critical tasks. All right, so that's fine about Morley, assuming that we can get working.
It should be working.
It just attached.
Oh, it got attached. Yeah, too. Okay. Thanks for the introduction. So actually, I'm going to talk about a few projects that I did over the last few years and trying to identify some principles in terms of how do we design measurement systems specifically for diagnosing problems on the internet and possibly also looking at attack defenses. So basically, I think motivation for measurement is pretty clear. We need really measurement to do a lot of things to understand how network systems are behaving. So we need to monitor things such as SLAs. SLAs are actually a poorly defined concept today for internet services because we don't really have really well-defined QoS metrics to understand whether the network is offering the service that we expect. A lot of times people just talk about availability, how many nines you have, but that's just a very coarse-grained metric. And oftentimes people also mention latency and loss rate across major POPs in a large ISP. But we all know that traffic usually traverses through multiple ISPs, so just having guarantee of a single ISP's latency is not sufficient. And we constantly need to monitor because we want to detect unexpected usage of the service or the network. So this gives us opportunities to react and adapt if things unexpected happens. And also gives us insight in the long run, how do we provision the networks better? Because a lot of times you ask questions to the ISP, how robust is your network be able to sustain various sorts of attacks? And they don't really have a good answer for you because they don't really know the kind of attacks they haven't observed, whether the network can sustain that. And those kind of questions I think is interesting to answer because you can configure and provision your network in different ways. And the cost of configuration is actually not very high, but we don't really have tools and mechanisms to reason how robust the networks, the current configuration are in terms of sustaining various sorts of attacks. And if you have a good idea of understanding of your network, how they operate, we can develop models and validate them when we come up with new designs of protocols. And so we can use those models to understand how those designs work in practice before deploying them. So this actually is the slides stolen from Jennifer's Rexford's work. She is saying that basically you have this operation network. You always have constantly monitoring going on, and then you have control, which is fed back based on the information that's taken from the network. So there are various knobs and dials which are in place. The dials are real-time operational kind of changes you can make to your network, and the knobs are changes that you can tune to your network. And in the end, you want your network to behave in a way that you expect. So the runtime adaptation idea is very important for various ISPs, and also for service providers which offer various network services. So I think network measurement is important, and it should be seen as a science. But a lot of times people build these network measurement systems, and they don't necessarily identify what are the lessons learned. So my goal is trying to understand what are these principles we can learn from various experiences of building these network systems. So I think Vern Paxton mentioned an interesting point related to when you measure actually in the presence of adversaries, it becomes much more challenging because the adversaries are trying to evade your measurement technique. And actually from end users' perspective, a lot of times when we measure, we try to understand how ISPs behave. The ISPs sometimes don't necessarily want us to know their internal details. So there's always some kind of struggle about the entities that want to understand the behavior of the system and the actual owner of the entity. Sometimes they don't want it to be the information to be revealed. So given this kind of struggle, given this kind of arms race actually for adversaries and the people who try to protect their systems, how do we design the measurement systems that are robust? I think that's an interesting challenge. And also we are trying to build a common measurement substrate for reuse because a lot of times we find ourselves rebuilding various tools and it's rather inefficient. So the dials we're looking at are essentially the input to the measurement system, to the adaptation system. So those data are collected, for example, from the network itself. For example, traffic information, which is link utilization, and net flow is a common mechanism to get flow-level traffic information. And performance can be collected through various measurement probes. And routing, which I will talk more later, is a very useful source of information to tell you how the control plane works on inside of your network. And this information is not always easy to infer, although there are lots of messages exchanged across routers. And once you have information about the measurement data, how do you change the parameters inside a network so that it can react appropriately based on the information, the state of the network. And we may discover that the knobs we have today are not sufficient. Maybe based on the information we have, we can learn that we can try to design better knobs so that the network can be tuned more effectively based on the information we can gather. So I will show a very simple example of how measurement can provide visibility in terms of the behavior of the network elements. And in general, you really want to understand a network from very many different vantage points and many different data sources. And be able to detect unexpected usage is very important from the measurement perspective. So we actually did some measurement where we of a real commercial router. What we found is unexpectedly based on the packet rate. So the left figure is showing the packet rate change and the bit rate change with respect to the actual packet size. So yeah, so as you can see, there's a sharp drop with respect to the bit rate and the performance through the router. So this is kind of somewhat unexpected. And later on, we also found the net flow sampling rate affects the packet rate. So there are these essentially artifacts related to the routers that we need to understand. This is a particular type of commercial router that other routers may not have similar problems, but things like this is something that you can discover through measurement. So, for example, we looked into detail of the architecture of the router design. So this tells us because the line cards have queues for different packet sizes, and because of that, you can design attacks which send very small packets, which could overflow the buffer queues of a particular designed for a particular packet size, and this would cause attacks which can create problems on the router without sending large rate of packet flows. So information such as this, in terms of how the router architecture is designed, influence the limitation in terms of sustaining different type of traffic. So this information is publicly available in terms of the actual router architecture design, but we actually conducted experiments to verify what type of packets at what, in terms of the packet size and what traffic rate can overwhelm a particular type of router. So I'm going to start talking about a few measurements system design in terms of the actual projects we conducted. In particular, 3 projects. One is looking at routing diagnosis. Second one is looking at spam campaign detection. And third one is looking at network neutrality violation. So a common theme across these 3 projects is that we have to do some reverse engineering. We built a measurement system mostly from the end user perspective. Actually, Jeff mentioned that I worked quite a bit with AT&T. And at some point, we felt like the data we get from AT&T is really valuable. However, it restricts us to the view of a single ISP. And it's also some unfair advantage we have. But the question is, how do we build measurement systems from end users' perspective? Maybe we can try to understand what limitations those measurement systems have, and essentially build these measurement systems from end user to understand how much we can infer from ISPs, from external point of view, and validate with the ISP. So by the way, if there's any question during my talk, feel free to interrupt. So the first piece of work I'm going to talk about is diagnosing routing disruptions from end systems. So this is joint work with Microsoft Research. Actually, so no AT&T involvement for this project. So the motivation from this work is that you have a lot of routing disruptions happening on the internet, some of which can cause severe performance degradation from end users' applications perspective. So it's useful to understand what kind of routing events cause what kind of performance degradation. Maybe you can assign a blame, say AT&T is causing significant disruption to your Skype session. So the question is, we can monitor these kind of routing events, but we don't necessarily understand what routing events cause what kind of data plane changes, which can have high impact on application performance. So for example, this is a simple route, and maybe there's some congestion happening along this path, and this router is going to experience a session timeout, and as a result, the packet may reroute. So existing approaches all focus on just getting data from the ISP, and what this means is that they can only focus on a particular single ISP usually, and they look at just the routing layer, essentially the control plane. So they don't necessarily understand how this directly affects the data plane, essentially the forwarding behavior of the traffic. So what we are doing is looking at, so this is the existing approach, just getting data from various routers, the BGP collectors, analyze the data, and try to understand what events are happening inside a single ISP usually. Because ISPs don't like to talk to each other in terms of sharing the routing data. They consider routing data actually as a proprietary source of information. So our approach is it's basically asking the question, can we infer these kind of routing changes from end users' perspective? In some sense, it should be pretty straightforward, right? If we observe a path from point A to point B, from like a probing host to a destination, if the path has changed, it tells us some routing state along the previous path has experienced a change. As a result, the path has also reflected that change. So our goal is trying to overcome limitations of ISP-based approach because we don't really have data from a lot of ISPs. Yeah.
What's an end system? Is it like on a residential DSL line, or is it like in a data center?
It's any kind of host. It doesn't have to be data center. For example, Planet Lab machine, any host here or DSL machine. So any host that's where you can run a piece of software to do probing. Yeah, it doesn't have to be a machine in the data center, which is connected to the high-speed networks. Yeah. So the motivation is that can we just infer the routing state changes, understand routing disruptions just by probing, simply probing. We all know this iPlane system. So can we deploy an iPlane-like system to understand routing changes that are happening on the internet? And as a result, we can assign some blame to the various ISPs, given some performance degradation we experience. Okay, so in this case, if there's, for example, a particular disruption, then we can observe accordingly the route change due to this disruption. Yeah, so the packets will reroute. So the goal is basically we build a system and continuously monitor the changes and compare any path measured consecutively along the same source destination pair. And if we want to focus on a particular ISP, we want to cover as many internal POP level paths as possible for a given target ISP. And we want to cover as many destinations on the internet as possible. So we have a particular target ISP in mind at any given point in time. Let's say we want to characterize AT&T to understand how stable its routing behavior is. Then we want to cover all its internal POP level paths if possible. And we want to also cover as many destinations on the internet as possible. So that's a simple goal. So I mentioned advantage and previously, because you don't really have to have access to proprietary data from ISP. And a second advantage is actually pretty important, we believe, because if you just observe BGP routing updates, it doesn't really tell you the actual forwarding behavior. Sometimes the BGP path has changed, but the forwarding behavior is not really disrupted. And because a lot of times BGP routes are aggregated, the actual detailed prefix routes may not be modified in any way. And sometimes the forwarding path has changed, but BGP routes are not affected. And also we can monitor the data plane performance using very coarse grained metric, for example, loss rate. By doing end-host-based probing, we can gather such information. And of course, the challenges are we have limited resources in terms of probing. We can't cover all possible destination source pairs on the internet. And there's a timing granularity associated with it. We can't cover each path constantly within short consecutive probes. We can send them within a very short amount of time because we don't have enough resources. And finally, we have measurement noise because the probing method we use is basically traceroute based. Sometimes the probes are lost because of ICMP rate limiting, so it's not due to performance problems. So we built this setup where we just do collaborative probing. So all of us are familiar with iPlane. So it's similar to iPlane in the sense that we probe from different sources to different destinations, given a target ISP. And then we combine the information together and understand various routing events and classify them into interesting events that we care about, which can affect data plane performance. And the third step is that we correlate these events across different locations so we can identify there's a particular routing event that has happened causing the routing path to change. Then we do impact analysis and generate a set of reports. So that's the overall architecture. So in terms of event correlation, we do both spatial and temporal correlation to understand the problems that occur together in time are most likely due to the same underlying cause. And a single network failure typically affects multiple routers. So in the end, we think there aren't many simultaneous events that are happening all at once. So that's our intuition behind how we correlate these events together to identifying the underlying physical reason that explain the path we observe, path changes we observe. Yeah. So for example, physical link failure that can cause the path to be rerouted, or the router has become congested, become unresponsive, so the routing session is reset. Yeah, fiber cut, right, which happens actually quite frequently. Yeah, Harsha.
Trace not only gives you the forward path, what happens when there are problems in the reverse path? Like, let's say different sources are...
So you mean the reverse path affected the trace route packets coming back? Yeah, so we do correlation, try to eliminate that explanation. So you're right. The probe response which comes back could be lost due to reverse path problems. Yeah. So that's one source of noise in the measurement. Did you have a question? No. Okay. Okay. So I'm going to briefly explain the inference methodology, which is actually a very simple technique. So we have these so-called evidence, which is an event, which demonstrates that there's some change happening in the network. So for example, you have two probing hosts and sent to the same destination, probes to the same destination. And all of a sudden, they switch to a new egress point, meaning that they exit the ISP to a different POP location. And one potential cause is maybe the link that previously was used, the inter-AS link is down, and as a result, that you switch to a new egress point. And a conflict is, so this is a so-called evidence, essentially an event that supports a particular cause. So this is one potential cause. It could be other causes. For example, you could have internal link weight changes, that meaning that maybe some links become congested, and their session could be timed out, and maybe these two paths share the same common link, and this link is no longer usable, then therefore they switch to a different link. And as a result, they switch to a different egress point. That could also happen. So so this is one potential cause for this observation that these two paths switch to a different path, in this case, different egress point. So then we have a conflict, meaning that a measurement that a trace, essentially, that conflicts with the cause. So it contradicts with our hypothesis that the link was down. So for example, previously we hypothesized that this link is down, but if you observe actual other path that actually goes to the link around the same time, you know that our conjecture that link L is down is not really valid, right? Because it conflicts with other observation. So in this case, if we do observe a path that actually goes to that link, that means that the link is not down. So this is just simply the conflict we have. So, yeah. This is after fact reasoning. Actually, our system is not that intelligent to do this adaptation. So we just have a set of destinations we continuously probe from each source host. Yeah, so an improvement could be that you observe something, then you gather more evidence related to that observation. Yeah, that's a good point. So so essentially, the inference methodology is we gather all these evidence information, and then we infer the potential causes. So we try to come up with a comprehensive list of causes that explain the evidence that we observe in terms of the routing event change. So each evidence tells us previously a path a previously used path is changed, switched to a different path. And so we have essentially a bipartite graph linking the causes to the evidence nodes. And then we also have the so-called, so this is an example of two evidence nodes and associated causes. So after we build this graph, we have this also the conflict graph, which tells us what are the which conflict nodes we have which contradict the cause we come up with. So essentially, we have two bipartite graphs. One is the evidence graph, which connects the cause to the evidence nodes, and the conflict graph, which connects the cause to the conflict nodes. So these two graphs gives us essentially is basis for our inference methodology. So our algorithm is a very simple greedy heuristic, which tries to find the minimum set of causes, which can explain all evidence while minimizing the conflicts. Right? So intuitively, we don't expect a lot of events that are happening on the internet, which occur at the same time within a single ISP. And we believe most of the evidences are due to only a few causes that we observe that are happening, which are the underlying reasons to explain the evidence. And we don't really want to introduce conflicts because conflicts are reasons where the evidences are false. But some conflicts are valid because we are probing at different times. So the evidences are gathered not simultaneously because we have a probing duration, probing round, which lasts for about 20 minutes, actually, for a large ISP. So within 20 minutes, things could have changed. That's why the conflicts could be introduced. So this is the key idea behind our inference methodology. Is there any questions behind this? So this is a very simple methodology we use. And in this case, for example, in this previous example, we can come up with two causes, right? The first cause would introduce more conflicts, and the second cause will have zero conflict, and we will pick the one with the lowest conflicts possible. Okay, so just quick explanation of the measurement actually validation we did. So we have the system running, and we studied a few large ISPs. These are some example ISPs we focused on, and we found essentially a few interesting points is the probing gap tells us how often can we cover all the paths within the ISP. So this means that events that last less than this amount, we may not be able to discover. So we are only focusing on long-lived routing disruptions. So in other words, if we want to be able to probe more frequently, actually it's likely due to the reasons that we don't have enough probe sources, and also we don't have enough computational resources from each probe source. Because we're using probing nodes from the Planet Lab, we can't probe very frequently because they're restricted in terms of bandwidth. And also we classified these different events. So some of these events that are interesting is, for example, we found in Deutsche Telekom, you have same ingress, egress, but the external AS path is different. This accounts to 80%, more than 80% of the observations, routing events that are within Deutsche Telekom. So this means that maybe they want to change their routing policies such that they are less susceptible maybe to external events. So this has implication in terms of what they could do in preventing those kind of routing disruptions. For other ISPs, the number is lower. For example, for Savis, the internal path change is quite significant, 45%. So this means that they have some internal instability. Maybe there are some internal unstable links. So when we go a step further, we can look at which are the link changes, link down events that could explain for this kind of internal path changes. So essentially, as you can see, that we can have these different categories of routing events. And from this information, we can come up with different traffic engineering improvements to reduce those kind of number of events that occur in the future. Because all these events affect the forwarding path. So this could affect your application performance if the application is using that forwarding path. Yeah.
Is this showing how you have two Planet Lab nodes and you're passing through the common system?
Right.
You're changing which router you're entering or changing which router you're exiting?
Yeah, so it's not just so we probe from the Planet Lab machines. We focus on those paths where we can traverse the target ISP, and we focus on just the segment of the path that traverse the target ISP. So we're interested in how we enter the target ISP as well as internal which POPs we traverse inside the ISP, as well as the egress points that we exit from that target ISP. Yeah, so we don't care about the path that is outside the target ISP. Yeah.
How do you determine the destinations for which the path will go through this ISP?
How do we determine? Okay, so we do initial analysis to use the, for example, BGP paths to get information. To do some, so we have to do some initial probing to figure out which set of paths are of interest. Yeah, we do it every day. Yeah, because I think those information is fairly stable. It doesn't change that often. You're right. So you have to do initial pruning because you don't want to send a lot of probes that don't traverse the target ISP. Okay. Yeah, so the internal POP path change is all due to the internal problems within the ISP. So that's good to identify. Yeah, we also did validation. So remember previously I talked about BGP previous methods all rely on BGP data. So our validation focused on a few of these key changes. One type of change is hot potato change. Hot potato is associated with egress point change due to internal distance change. So this means that internally you have a link down event or some events which cause your internal path cost to go up. So as a result, you switch to a shorter path because you're doing shortest path routing inside the ISP. And because you switch to a shorter, a cheaper path, and the egress point can change, then that usually causes significant traffic shift. And your neighbor ISP may not be too happy either because all of a sudden you're shifting a large amount of traffic from one egress point to a different egress point. So we did validation. As you can see that the number of incidences identified by BGP methods is 147. So our method is able to identify more. So this means that BGP method is not necessarily always accurate because there are a few other ones that are missed. And there's a common set of them. So 101 is the set that identified by both of us, both methods. Okay, so we have a few positive and false negatives. So the false positive and false negatives are, some of them are inevitable because just the methodology inherently are different because the data sources we use are different. So we also validated looking at session resets, which is another interesting event that people focus on because it affects significant amount of traffic. So in conclusion, this is a sort of an experiment we did trying to understand, can we really do something to infer routing problems inside the ISP without really having any access to proprietary data? So the answer is that we can do I think fairly decent job given that we have limited resources from Planet Lab, and our system is a online system, so you can continuously monitor the changes that are happening inside a given target ISP. And using this information, maybe we can make suggestions about, in terms of traffic engineering improvements, and also maybe in terms of overlay routing, you can also have information about which paths are less likely to be stable. And our technique is just relying on a simple greedy heuristic using two bipartite graphs to infer the causes of what's going on. And we validated accuracy to some limited extent because we don't really have ground truth. But given that it does match a majority of the events we identified did match with BGP inferred causes. We're fairly confident that what we found is actually accurate. And also remember that BGP inferred events are not necessarily observed by us because it's purely at the control plane. Because BGP updates tells you the routing path has changed, but the data plane path information is not directly available, right? Because we are just doing actual probing to give us more accurate information of what the path is traversed by the actual data packets within the ISP.
Question.
Yeah.
So when you, just to clarify, when you say validated, you mean against BGP data?
Yeah, that's what we did.
So you never talked to AT&T and said, this really thought that you're out.
We used the data from AT&T actually, and from a large ISP. So in other words, we use their BGP data. So their BGP data tells us the control plane routing events, but we don't really know. So session reset actually we validated from the syslog. So this tier 1 ISP, we get this syslog information in terms of session reset. So different events you can validate through different ways. So of course you're saying, so the BGP-based method itself has validation, has its own set of validation techniques behind it. So for example, session reset, you can get information from the syslog data from the routers. And hot potato change, you can get information from the OSPF data in terms of link down and link up events. So that's a different type of validation.
And so the false positive and false negative means against what ground truth?
Against ground truth of BGP-based. Yeah, so we don't really have perfect ground truth because BGP data, so the problem with BGP data is that sometimes BGP events are not visible by us because we're probing at very coarse grain level. And also BGP events do not necessarily reflect forwarding path changes.
But if you had access to syslogs, then why didn't you use syslogs for the actual link state?
She did.
Yeah, we did for, yeah, syslog. But syslog still doesn't tell you how traffic is going to be changed, right? How the path of the traffic is going to be changed. So it's only to a limited extent. Yeah, we did use syslog for session reset, for example. Yeah, right, for BGP sessions.
So for both of the validation experiments,
Right.
there's some that BGP missed,
Mm-hmm.
there's some that your method missed.
Right.
What's the potential for there are other events that both, is there any way to evaluate events that both techniques missed?
Right, I think it's possible. So one type of events we missed is because we don't probe that often, so we don't cover as many paths and all the time. So those we definitely miss. And there could be, that's the only source I can think of because our way of monitoring, if you care about data plane path changes, our methodology, I guess another thing is traceroute has limitations, right? So sometimes maybe if you believe the traceroute path is indeed the data plane forwarding path, then traceroute should give you that information. But sometimes the return path could affect our observation too, because the return packets could be lost. So in that case, we don't get information of the path for that particular probing. So there's limitation due to the probing methodology.
I have another question about, for example, fiber cut, right?
Mm-hmm.
So, and then connection to the reuse approach. Then, for example, when fiber is cut, there are too many network layer links that may be multiplexed,
Right.
right? Therefore, one single physical event may actually lead to multiple network.
Mm-hmm.
Then 3D approach,
So if fiber cut is the cause, so we will see that link down is one cause, right? So
it's not link, it's mainly link, because the fiber cut are mainly network layer links because they're multiplexed.
are you saying that actually the link is not down? It's just the logical link is not down. One of the physical links is down.
No, I mean the fiber is cut, there are many links.
Many links, yeah, sure. So what does this reflect in terms of the forwarding path? So we don't diagnose all possible changes, right? So if one link is down, but the other links are still up, between the two routers, they can still communicate. right? So we don't diagnose the performance. So we can talk it offline. Yeah, so to answer Jeff's question, I guess there are a set of events we don't diagnose. It's not covered by the BGP method nor our method. I think some of them are due to the probing granularity and also the probing tools limitation. But in theory, if you can monitor a path continuously all the time between source destination pair, then you should be able to observe all possible forwarding path changes. I think that's sort of something that we depend on. Yeah.
If you have more plant labs, is that feasible, or would you start running into either technical or policy problems with the ISP?
I think the ISPs won't notice this unless they stop responding with ICMP response packets. So far, big ISPs haven't disabled ICMP response packets, but some of the ISPs are MPLS enabled, so you don't observe anything internal to the ISP. So for example, they just use, all you see is just ingress point and egress point. So for those cases, we can't infer anything internal to the ISP. So I think Quest is one such ISP for which the trace route simply doesn't work. So you don't get information at all. Yeah, so that can be reduced. Yeah, but like I was saying earlier, ISPs can prevent us from working altogether by disabling trace route response to our packets, right? So they could still let trace route work from their management prefixes, which they want to have trace route to work for debugging purposes, but they could just disable trace route for any other packets, any other source packet. Yeah, so this definitely has limitations in terms of what we assume the ISP would support. What kind of, they should be able to respond to our ICMP, or they would respond to TTL time exceeded message if they see the TTL value is decrement to 0. If they don't do that, then we don't have any information. So I'm going to switch gear a little bit, talk about a different piece of work we did. It's also, I'm going to quickly talk about this, actually, given the lack of, it's only about 15 minutes left. So this work is actually also, I think the theme of the project is also what we can do, what end user can do just by probing the internet. So here we're trying to also build a reachability graph. So from previous project, you can basically summarize that each end host is building some kind of path information or reachability graph to the different destinations. And we focus on a particular ISP. In this case, we don't really focus on particular ISP because we're focusing on the project. The goal is to detect prefix hijacking. So the problem is that you have a particular prefix, you own one, and you don't really know if other people are using it, right? If someone else announces it as if they own the prefix, then that means that packets could be routed to that location instead of back to you. So that could cause serious reachability problem. So for example, in this case, I have a prefix 4/8, which is an artificial prefix. And see, the attacker also announced it. And given that the routing architecture today do not really do any validation, authentication to see who owns which prefix. So this kind of attack could happen either due to misconfiguration or malicious intent. So if that happens, then you have two sets of routes. One set of the routes are the valid routes, which will go back to the actual owner, which is the victim in this case. And the bogus routes will get to the attacker's network location. So this is quite serious because it actually means that you cannot reach certain destinations. Actually, destinations on the internet cannot reach you. And this also means that you cannot reach them because you require them to talk to be able to reach you in order for bidirectional traffic exchange to happen. So this is a problem, and a set of networks on the internet today will get polluted because they have no idea which set of routes are valid. So unfortunately, internet today doesn't have a good way to deal with this problem. Ideally, you would think that each router, each ISP would have a authenticated, validated list of prefixes of who owns which prefix. Then this partially solves the problem. But however, we don't have such kind of authoritative list of information of the ownership of prefixes. So most of the existing approach is infrastructure-based for hijacking detection. So we resort to detection usually when things like that happen. People try to detect it and then react to it. So infrastructure-based approach has a few shortcomings because accuracy really depends on the coverage in terms of where you can observe these various routing updates. And it's not easy to deploy because you rely on getting BGP data. So this is another source, the same source of data that we rely on in the previous work. And BGP data is not actually easily obtainable from various networks. And there's no incentive to deploy this kind of detection. And also, once the attacker, once you detect some attacker, there's no easy way to notify the victim because at that point, the victim is not reachable. The prefix it uses is stolen by some other attacker AS. So it's not always easy to reach the victim. Did you have, was there a question? Okay. So what we come up with is a very simple technique. It's basically asking the victim itself to monitor its reachability, right? So all you care about is, can other networks reach you? And what you can do is do some lightweight probing. And you can build a reachability view of a graph of how other networks can reach you. And using that information, you can potentially detect problems associated with prefix hijacking or some physical failures. And those problems could explain, those symptoms can explain whether your prefix is being hijacked. So our technique has more advantages. And the key observation is that a hijack of a prefix X can cause a significant of the internet to be polluted typically because everyone will near the attacker AS tend to adopt the route announced by the attacker AS. Because usually the internet routing policy is that you want to pick the shortest route to reach to a destination. If the attacker announces a route to a particular destination, networks close to it will think that this route is more attractive because it is close to the attacker AS, right? So that's why typically you will have a significant fraction of the internet that will get polluted, will be affected if hijacking happens. And also a significant fraction of probes sent out from the prefix X to the internet will not come back. So this is essentially from the probing perspective. If you are monitoring your own prefix, the reachability of your own prefix, then you will see that a lot of these networks cannot reach you. You won't have a response because you are sending packets to those networks. Previously, you get a response back, and all of a sudden, you can't get any response back. So the second observation is directly followed from the first observation. So we exploit these two intuitions by designing our system. So our challenges are basically how do we distinguish reachability problems caused by hijacks from other events? Because you could have a reachability problem due to, for example, congestion, packet loss due to physical failures, link failures. So we essentially build a reachability view from the prefix owner's perspective, and we build this view and develop this concept called cut. Cut essentially identifies a way to distinguish the hijacks from other events. So, for example, here's the prefix owner. It does traceroute-like probes to the various destinations, and it translates that path into AS-level path. And over time, the prefix owner builds a reachability view in terms of how it reaches the rest of the internet. So the cut is basically what separates between the reachable part of the internet and the unreachable part. So if you can distinguish, if you can have a small number of cuts, that's more likely that you have a physical failure type of events. Because usually, if you have a single physical failure, those networks which are impacted tend to be localized in terms of topological location. Whereas pollution due to hijacking is likely to be more widespread. So that's the intuition behind it. So the left part of the picture shows the scenario where the prefix hijacking happens. And the right part is example, it's more likely to do a physical failure. Of course, you can have a prefix hijacking event which is very localized in its effect. That could also manifest itself in the right graph. But yeah.
So if you knew that you were going to look for the signature to distinguish a prefix hijack from a cut, couldn't your adversary, who wants to look just like a normal cut,
Right.
then I will put the ASs of all the other ISPs who I do not want it to be hijacked.
Right. So essentially, you prepend the path to contain.
Because of the loop avoidance, and then I'll look like that one on the right.
Yeah, they could do that, but usually the goal of hijacking is you want to pollute as many ISPs as possible. You're right. So they could construct the path announcement in a way that maybe introduce this kind of scenario. That's possible. But I think in general, attackers are not that smart. They don't necessarily do that. And I'm not sure, I guess, what's the motivation? I guess they don't want to be detected by, as seen as a prefix hijacking case.
What you want to do, right? If what you're doing is casting a very, very broad net, right?
Mm-hmm.
I want everyone who goes to Bank of America to come to me. You're absolutely right. Then they'd like to get it out there as far as possible. What they're instead trying to do is if they are, doing the spear phishing or the equivalent, they're going after one organization, then they would like this organization to see, a particular IP prefix as something else.
Right, so if they have a targeted set of victims that they don't necessarily want widespread effect to occur. Yeah, I think that's a valid point. This can happen. Do you have a question in the back?
There have been some people who have done BGP man-in-the-middle attacks where you maintain one return path by appending or by putting that particular AS on the return path, and then you can actually route all traffic through and then back across the web path.
Right, so I think a lot of times what they do is they do check that the routes you announce from your provider, from your neighbor, they verify if those routes are, I guess in that case, you could append anyone else's ASs, right? So the trick is that you don't really have to, you can modify the AS path so that other people's ASs are contained in this path. Yeah, so Stefan's suggestion is the same. So you essentially have a route which has your own AS number in it, but it will be rejected because it will be seen as a loop. But there should be some routing anomaly detection mechanism that could detect that. All of a sudden, you see some routes that are previously topologically doesn't make sense because ASs will be, you will detect AS level links which are previously non-existent, right? Yeah, did you have a question? Right. Yeah, I think you can.
It's like Egypt got separated from the internet or whatever. Do you think that would be on the move? So it seems like more straightforward to detect these targeted prefix hijacking.
Right. So another goal we have is that given this kind of graph of reachability, can we identify where the victim, where the source of pollution comes from, where the attacker AS is in terms of where the hijacked routes is injected. Because it's not always obvious that it's part of the AS path that is announced. Sometimes they can inject a route that doesn't contain the target AS, the attacker AS. Yeah. So I think I'm going to try to wrap up. Yeah. So actually, the common themes that we also build this graph, reachability graph, which is very useful, I think, for various purposes, either diagnosing routing hijacks or hijacking events or various failure events. So I guess the one thing I want to point out is that this kind of probing is very similar to what we are doing in the previous project. And also we applied similar type of probing to detect neutrality, network neutrality violation inside ISPs. So this is actually, I just want to show you. I think I had a slide which with the results of which ISPs are violating network neutrality. So basically we did probing from various locations which has these network, which has this, our focus is to understand our focus is to understand whether ISPs could violate network neutrality in terms of treating packets differently depending on the packet content, application content. So we found that essentially we send packets of different type with different type of payload. and to understand whether ISPs treat them differently compared with HTTP as a baseline. We found that there is, with different ISPs, actually there is non-significant fraction of path pairs that do experience differentiation in terms of, so we compare the loss rate distribution as a way to detect whether packets are treated differently. And although the percentage is low, it just means that they may not deploy this differentiation ubiquitously within their ISP. But there is some evidence that we found that tells us that this could be something that they are instrumenting inside the ISP to prevent, essentially to prevent unfair resource usage from those P2P applications. Okay, just so to summarize, I think what I've shown you is various probing methodologies which are entirely constructed from end-host perspective. So I think there is still a lot of research to be done in terms of what measurement tools we can develop given limited support from networks. And we do want to have better real-time decision support because as we detect various unexpected usage of the networks, the question is how do we adapt the networks in real time so that we can offer better performance guarantees over time. And actually, I have some ongoing work which I can talk to you offline, which we are doing for monitoring data center networks as well as data cellular networks. Yeah, so one application we have developed is for people to download from your, we just posted one application which iPhone users can download, and we're asking people to measure essentially your network performance depending on where you are, so we can collect various data in terms of how ISPs, how cellular ISPs are blocking various ports and how they can give differentiation to various applications. I believe they have more incentive than internet ISPs because cellular data services are much more, the resources are much more oversubscribed. Yeah. Yeah, and for example, we found that one interesting observation we had is for the AT&T 3G service, if you use iPhone versus HTC phone, you actually experience different data paths. For the HTC phone, they go through a particular proxy, and it's always deterministic through the proxy, at least from the Ann Arbor location. So they probably do something weird at the proxy level, maybe. But for iPhone users, they don't do that. So essentially, they do device-specific traffic differentiation, at least at the coarse grain level, in terms of whether your traffic goes through a proxy or not. Okay. Thanks.
And we have time for questions. I have one.
Yeah.
So I was actually very interested in the final results for your traffic hijacking, your ISP, your prefix hijacking.
Right.
So how often does it happen?
How often does it happen? We found it, so there are some false positives, but we do find cases where people didn't, so we believe those are hijacking based on our observation. We found like once, depending on which prefix we monitor, we found some cases like once every 2 months, those cases.
Were specific prefixes targeted, specific, later numbers than others? Was there a favorite target?
You're looking for malicious hijacking.
Yeah, we don't know if it's malicious because some cases are very transient. You see them. Okay, one case we found is validated with the BGP routes. We believe it's a misconfiguration. So we're in the BGP announcements, we do also observe these paths are mistakenly announced. Then they are withdrawn, subsequently withdrawn. We were able to validate with the reachability view analysis from the probing. Yeah. So our goal is to set this up as a web page so we can have this information available so that people who are interested in this, if they observe some reachability problems, they can at least go to the web page and check it out and see potential list of ISPs. Yeah, the problem is that we don't really want to point fingers to ISPs who may be our false positive list. But it's useful, at least as a candidate set, that could be those ISPs that misconfigured their network, which announce those prefixes incorrectly. Right. So
Do you think that's the predominant cause of working measure?
misconfiguration. Yeah, I don't know if any of them are due to malicious intent. We try to correlate spam information with the what we observe as hijacking, but we found very small correlations, so we don't really have strong evidence. I know Nick Feamster's paper at some point showed there is some /8 level hijacking, but that seems very unusual. I don't know if spammers are really using this kind of technique, because it seems much more overhead, right? Because you have to be able to find a compromised router to announce those malicious routing updates. So I'm not sure this is actually done by spammers, for instance. Thanks.